Hello, my name is Jared Skeens. Welcome to the Zoom room. Today we want to look at a Pure Maths 3 past paper, May, June of 2020, paper 32. So this is Pure Math 3 from the Cambridge A-Level. And these are worked solutions that I will take you through and hopefully will help you with not just how to do the problem, but how to think with regards to reading the question and setting it up. So let's get started. Here we have our first question. Find the quotient and remainder when 6x to the fourth plus x cubed minus x squared plus 5x minus 6 is divided by 2x squared minus x plus 1. Now this particular question comes from the further algebra section, and more specifically usually is found in with like your remainder theorem and factor theorem. But in this case, it just asks a straightforward division question. So you can use long division if you want to. I teach synthetic division simply because it's faster, and in a Cambridge exam, notice it's only worth 3 points, meaning you only have about 4 minutes to do this problem, and you don't really want to spend a lot of time writing out all these variables over and over again. So you're going to have to use the method that you're used to. If you're not familiar with synthetic division, I highly recommend it. Basically, other than some simple procedure things, basically it boils down to place value. So here we have x to the fourth, that's our quartic place value. Here's our cubic, here's our quadratic, here's our linear, here's our constant. So just take the coefficient 6, 1, -1, 5, -6, and then the divisor is a quadratic, 2x squared minus x plus 1. By the way, if you're missing an exponent, you do need to hold its place value with a 0. So make sure all of your exponents are represented. Anything that might be missing, you'll use a 0 for. In this case, they're all given. So with the divisor, we start over here on the left, and we use the opposite sign. So we're going to start on the inside and work our way out. So this +1, we're going to make it a -1, and this -1 here, we're going to put it on the next row below over a little bit, and that's going to be +1. If your first term has a coefficient of 1, you don't need to worry about it. So you wouldn't have a third column for it if it had a coefficient of 1. Since it has a coefficient of 2, we need to put it down here at the bottom as divide by 2. So we're going to draw our lines this way and this way. Here's the dividend up here. Here's the divisor, working our way out in this diagonal here, except for the 2. If you wanted to, you could put it out here, divide by 2. I just put it here. Here's our line. So we bring down the first term. It's a 6. Now, since we have the divide by 2 here because of this coefficient, we'll go ahead and divide it by 2, makes it 3. 3 times -1 is -3. How do we know it goes here? Because we're 3 terms deep, so we need to go 3 terms deep. 1, 2, 3. Then the 3 times 1 is a 3. That's 2 terms deep. So we need to go in 2 terms, put the 3. Add this column, we get 4. Divide by 2, we get 2. 2 times -1 is -2. 2 times 1 is 2. Add this column, we get -2. Divide by 2 is -1. -1 times -1 is +1. -1 times 1 is -1. Add these 2 columns. Now, how do we know where the remainder goes? This is a quartic divided by quadratic. So 4th power divided by 2nd power is 2nd power. So this 3 represents the x squared column. Here's the x column. Here's the constant. Everything after the constant is remainder. And yes, the remainder can have more than one place value. And notice that with the remainder, we do not continue to divide by 2. So you only divide by 2 into the whole number parts that you get, but for the remainder part, you stop dividing by 2. You still add up the columns, and we have 2 and -5. So what does that mean? Means that the quotient is 3x squared plus 2x minus 1, and the remainder is 2x minus 5, where the -5 is the constant, and the 2 is the linear, or x to the 1 power, first degree term. Okay, so that's how we do that. So again, you can use long division if that's what you learned, but I prefer synthetic division. You can probably do this in half the time as what's given here and use it for somewhere else. Number 2, here is what was in the logarithms and exponentials in what they called modeling. So you have a graph that originally would have been curved. Your original xy would have had some sort of a curve, either a power curve or an exponential curve. And by taking the ln of the y values, it flattened out the curve into a line. So they've graphed this after they have already flattened out the data from an exponential into this linear graph. Now, in the problem, it says the variables x and y satisfy the equation y squared equals ae to the kx. So here you see your exponential where a and k are constants. The graph of ln y versus x is a straight line passing through these two sets of coordinates as shown in the diagram. Find the values of a and k corrected to decimal places. Now this one is a little bit tricky. Normally you can do one of two things. You can either work from the line, that is the y equals mx plus c, and you can work to the equation that you want to develop. This equation being the equation that models your original data points, or you can start with this equation and work your way to the straight line. Now, normally, if you were to do this in, say, like a science experiment, your data points don't come with the original equation. So usually, you're going to try to flatten the curve by taking the ln of either y or both the y and x. And you're going to start with your linear equation, and you're going to develop your formula for your original data points. In this case, they provide for us the equation. So we have the opportunity to work both ways. In this case, I would not recommend going from the linear to the equation. And the reason is you need to introduce two different things. You need to exponentiate both sides base e, and you also need to square or somehow introduce this square into your equation. Now, I'm guessing that most of your teachers probably have not expressed how to do your order of operations between a transcendental function like exponentiating both sides and an algebraic operation such as an exponent. So maybe your teacher has mentioned the priority or the order. Maybe they haven't. I'm going to guess that your teacher may not have. So in that case, I would go from the equation here where they're both already present and then work to the line. So that's what I do here in the work. I start with the equation and we want to work back to the line that is represented in the graph. And So the first thing that we're going to do is we're going to ln both sides. Notice when we ln both sides, you can then use your law of logarithm to move the 2 to the front. And actually this point right here might give you a clue on how to introduce the square if you were working from the line to the equation, that this would be how you would introduce that square. It's not necessarily from squaring both sides, but basically multiplying both sides by 2 on your logarithm. But here it comes to the front. Over here, when you ln both sides, remember, multiply in your law of logarithms separates out to an addition of like logarithms. Then over here, the ln and the e cancel, giving you your kx. And here you can divide the 2 to the other side so that you get ln y by itself, which is what you want because you have ln y as your y-axis. And so you end up with k halves x plus 1/2 ln a. This fits our y equals mx plus c, where the k over 2 is our slope and the 1/2 ln a is the plus c. So to figure out the plus c part, or this 1/2 ln a part, we need to plug in an x and y coordinate. So I picked the 1.5 and 1.2. Now remember that the 1.2 is not just the y, it is ln y. So be careful there that you're plugging 1.2 for the entire ln y. Don't put ln 1.2 because it's already identified as ln y on your y-axis. So this is 1.2, your x is 1.5. This is the x-axis here. And then your slope, you can figure out manually using your change in y over change in x formula. Your simple algebra formula for slope, y2 minus y1 over x2 minus x1. And we see that the slope is 0.401. So we replace that k over 2 with 0.401 because that's our slope. And then when we calculate all of this out, the 1/2 ln a comes out to 0.5985, which is then our plus c in our linear format. So this is our complete equation for the line of this graph up here. And now we can solve for the k and a. The k over 2 is equal to the slope. Multiply both sides by 2. The k is equal to 0.80. The 0.5985 is our 1/2 ln a. So multiply both sides by 2, exponentiate both sides base e, and a equals 3.31 to 2 decimal places, which would ask for. So while this equation up here is the equation that would model your actual data points, now that you have k and a, you could plug those in up here so that you could then model future predictions for outcomes. Okay. So that's how you do that. Moving on to number 3, find the exact value. Notice I double underline exact. That means we cannot use decimals. We need to use radicals or the pi symbol, something like that. Now, when we look at it, it says integrate. This is x to the 3/2 power ln x dx from 1 to 4. So this is going to be integration by parts. How do we know? Because you either have a product rule, a product, or a quotient of unlike math. When I say unlike math, see here we have an algebraic term and a transcendental function. That's what I mean by unlike math. If you had like 2 algebraic terms, you could combine them and do it differently. But we have algebraic and transcendental function, and separated by either a multiply or a divide. That's when you're going to use integration by parts. Now the trick is picking the parts correctly. You're choosing U and dV, which, by the way, you can go to my video on integrating by parts, and it explains how the formula is derived. I don't want to take that time now, but I will mention, how do we choose the parts? How do we choose the U and dV? Normally, you would use the x to the 3/2 or x to a whole number as your U, because when you take the du, it simplifies down. But in this case, we can't do that because our ln x, we don't have an integral for our ln x. So since we cannot integrate our ln x, it needs to go into the u. And it does turn into an algebraic term when you derive it. So the ln x needs to be the u because it can't integrate, or at least with our Cambridge formulas that they give us, we don't have an integration for it. So we're going to put the algebraic part as the dv, the ln x as the u. Now we need to take the du, which is the derivative of ln x, as 1 over x dx. We need to integrate the x to the 3/2. Remember, you add 1 and then divide by that number. So when you divide by 5/2, means multiply by 2/5. Now that we have our parts, now we can put the parts together according to the formula. Again, if you don't know the formula, you can go to my Cambridge A-level. This would be an integration by parts, and you can watch the video to see where this formula comes from. But we take u times v. So here's our u times the v. I put the algebraic in front, minus the integral of v du. So here's the v and the du. Notice one of the x's cancel since it's multiply. So 5/2 minus 1 is 3/2. We still have the 2/5 in front, and don't forget the dx in the back. So now, even though this is still a product of unlike math parts, there's no integral anymore, so we don't have to worry about this. Our integral is now with the algebraic part, which we can do. And so we just add 1 and divide by 5/2. When you multiply by 2/5, you get 4/25. And now we're going to, and don't forget the minus out here, we're going to evaluate now all of this from 4 to 1. So when you plug in a 4 into these, you get 64/5 ln 4 minus all of this comes out to 128/25 minus, then you plug in a 1. When you plug in a 1 into ln x, that makes 0. So this first term cancels out. When you put a 1 in here, you get 4/25. So notice we have this minus is because you do top minus bottom, and then this minus comes from right here. So don't forget you have 2 negatives here, not just 1. So that changes that to add. When you combine the negative 128/25 and add 4/25, you get a negative 124/25. The 4 can turn into a 2 squared, which the exponent then multiplies to the front. And so we get 128/5 times ln 2 minus 124/25. Remember, it wants exact value. We can't use decimals, so this is as reduced as we can get. Moving on to number 4 here, a curve has an equation y equals cosine x sine 2x. Find the x-coordinate of the stationary point in the interval from 0 to pi/2, giving your answer correct to 3 significant figures. So let's go to the interval first before we forget. Notice the interval is in radians. Since we're dealing with trigonometry, make sure your calculator is changed to the radian mode for this question. So whenever I see the domain like this, I write or degrees, and I set my calculator right away so I don't forget. And I also take note of what quadrant is or quadrants are allowed. In this case, it's just a first quadrant answer. Now let's get back to the question. The question is asking for the x coordinate of a stationary point. Hopefully you remember from your P1 material, stationary point is the first derivative equal to 0. So we need to do the first derivative, and when we look at this, this is a product rule. We have a cosine x times a sine 2x. So we're going to do the product rule. I'm just going to use y prime as our notation for taking the first derivative. So here's 1 d2, the derivative of the second, which don't forget to take the derivative of the inside of the argument, which is another 2, plus second term times the derivative of the first term. The derivative of cosine is negative sine, and we set it equal to 0. So when we simplify things, multiply 2 to the front and put this negative in the front. Now notice there are these double angle identities. So it might be, how do you know which one to use? Well, I'm going to start at the back here, and this sine 2x, there's only one identity that you have for that. So that's 2 sine x cos x. Now, when you look at the front, the cosine 2x has 3 different identities that are in your formula sheet. So when you look at it, you want to look at what's common here. We see there's a factor of 2 common. We see there's a cosine common. So what we're going to want to do is we're going to change it into sine, the one that just sine. So I picked the 1 minus 2 sine squared x, and then distribute. So 2 cosine x times 1 is 2 cosine x. Multiplied by here, you get a minus 4 cosine x sine squared x. Minus all of this is 2 cosine x sine squared x. And then you can combine like terms. Both of these have a cosine x sine squared x, which makes a negative 6 cosine x sine squared x. Now factor out what is common for both. Don't divide everything by cosine to make your cosine disappear into the 0. When you are solving, you don't want to cancel out a variable you're solving for. Now, if you did that, it wouldn't hurt you on this equation, but that's a bad habit to get into. Don't multiply or divide by something that causes the variable that you're solving for to cancel out. So if you divided by cosine x, it would make that particular x cancel out, and you would lose these 2 values right here, which happen to be outside the domain. So we're going to throw them out anyway, but you don't know that at this point right here. So we want to factor it out, not divide it out. So there's a 2 cosine x common to both terms. That leaves us with a 1 minus 3 sine squared x in the parenthesis as the other factor set equal to 0. 2 cosine x equals 0, divide by 2, cosine x equals 0. Now notice dividing by 2 is okay because you're not losing a variable. That's what's important. If you can divide to cancel out the 2 and it goes away into the 0, that's okay because you're not losing a variable, but don't do it with the cosine x up here. Right here at this point, don't do that. So cosine x equals 0. Where does cosine x equals 0 at? It equals 0 at 90 and 270, or at the pi halves and 3 pi halves location. And when we look back up at the domain, obviously 3 pi halves is too much. And even though it says pi halves, there's not the equal to. So both of those get thrown out. Over here on the left, solve this one. And when you get it down here, sine squared equals 1/3. Square root both sides. Don't forget the plus or minus. Okay, that gives you Normally, sine is positive in 2 quadrants and negative in 2 quadrants. So don't forget to put the plus or minus. This does give you 1 through 4th quadrants. However, because of the domain, we're only going to take the first quadrant. But you still want to practice good math. So don't forget to put the plus or minus on when you square root both sides. So when we do the inverse sine, I didn't show that step, x equals the inverse sine of square root of 1/3, you get 0.615. This is in the first quadrant, and you don't have to go through and find the other 3 quadrants. So 0.615. Moving on to question 5a, here's another trigonometric expression that we want to change over into this r cosine x plus alpha form, where r is greater than 0 and alpha is between 0 and 90. Again, give the exact value of r and the value of alpha correct to 3 decimal places. So to find r, it's basically like using the Pythagorean theorem, where you use the root 2 and the negative root 5, although the negative doesn't really matter because you're squaring it. And so you have the square root of root 2 squared plus root 5 squared, which gives you the root of 2 plus 5. Don't cancel out the radical with the exponent. Radicals do not distribute over add and subtract, so you cannot cancel those. You have to work out the exponents on the inside of the radical. You get 2 plus 5, which is 7, so you have the square root of 7 for your exact value of r. Then for tan alpha, you take the b over the a. This second number is your b, the first number is your a, the b over the a. So we have negative root 5 over root 2. Take the inverse tangent, and it actually gives you a negative 57.688, which is a 4th quadrant answer. We want the first quadrant answer, so we'll just move it up into the first quadrant. 57.688 is our first quadrant answer from that reference angle. And so our final form, root 7 cosine of x plus 57.688. Remember, it said 3 decimal places. And here's r specifically and alpha specifically for the answer to the question. Moving on to part B, hence solve, and it gives you this equation. Again, now notice they changed the domain to degrees, so make sure you set your calculator back to the degree mode, and our domain is for first and second quadrants. Now, the word hence means there's something we need to take from the question we just did. If you look at this original expression and you look at this one here, they are exactly the same thing except for the 2 theta. So we're going to take our result right here, the root cosine x plus 57.688, and we're going to use that, except instead of x, we're going to use 2 theta. So everything else we take from the previous question, and we just substitute in the 2 theta because that's the only difference. And don't forget the equals 1 on the right. Now this is basically a algebraic solving until we get down to the trig part. Divide by root 7. 1 divided by root 7 is 0.3780. Now we need to do the inverse cosine, and this is positive. Cosine is positive in the first and fourth. So inside the parenthesis, 2 theta plus 57.688 equals, here's our first quadrant answer, here's the 4th quadrant answer. So 67.79 is our reference angle. It's also the first quadrant. When we put that into the 4th quadrant, we get 292.21. Then we subtract the 57.688 from both of these, That gives us 2 theta equals 10.102 and 234.522. Then divide both sides by 2. That gives us 5.051 and 117.261. Normally, we would do an interval. Notice there's a 2 theta. That means there's 2 cosine waves between 0 and 360. So if we figured out the interval 360 divided by the 2 means that the interval between this set and the second set is 180 degrees. But if we add 180 degrees to both of these values, it will be over the domain. So we don't really need to do that because it extends us over the domain. But these two answers that we have here, 5.1 degrees and 117.3 degrees, are between 0 and 180. So that's our two answers there. But you should be prepared to get 2 more answers from the interval. Don't forget the interval, sometimes those are used as well. Question number 6, here we have this graph. Don't know if you can see it well in the video, but this part right here is the shaded part, and it sometimes doesn't show up very well when you scan it or do photocopies. So the diagram shows a curve with this equation, calls M the maximum point, wants us to find the x coordinate of M, giving your answer correct to 3 decimal places. So if you're finding a maximum point, you're going to set the derivative equal to 0. Now, if you look at the equation, it is a quotient rule. We have an x on top, we have an algebraic on top. We do have an algebraic on bottom. I know I just said earlier that usually it's between different functions of x, like algebraic and transcendental. These are both algebraic, but they can't be simplified. In other words, you don't really want to be dividing the top by the bottom. If the x were on the bottom, then you could simplify it and not have to use the quotient rule. But since the x is on top and this is on the bottom, we can't really simplify this. So we're going to use the quotient rule, where we have low d high minus high d low all over the square of what's below. This formula, by the way, as well as your product rule and the quotient rule, are both in your Cambridge formula sheet. So you can look at that to help you if you don't remember. But it's low d high minus high d low over the square of what's below. Then in this case, it's okay to multiply this 1 plus 3x to the 4th squared into the 0 because it is a part of the numerator, and your 0 is, you don't have like the denominator aspect to work with this. So it is okay in this fractional situation where the numerator is equal to 0 that you don't have to worry about the denominator. You can cancel it out into the 0, multiply it to the other side. Normally, like I mentioned before, you want to be careful eliminating a variable. In this case, it is okay because it's the numerator that's equal to 0, not the denominator. So distribute through your numerator here. 1 times this is just the 1 plus 3x to the 4th, minus, you get 12x to the 4th. Now these combine to give us 1 minus 9x to the 4th equals 0. Move the 9x to the 4th to the other side, set it equal to 1. Divide by 9, 4th root both sides. Again, because it's an even root, you need the plus or minus. Although in this case, m is obviously on the positive side of the x-axis, so we just take the positive 0.577, but you still should put plus or minus because it is an even root. So 0.577 is the x-coordinate of point M, which is a maximum. Now part B, by using substitution, find by integration the exact area of the shaded region bounded by the curve, the x-axis, and the line x equals 1. So that means we're going to integrate y equals to the integral from 0 to 1 is our boundaries. Notice that the graph started at the origin and ends at 1. So 0 to 1 are the boundaries of our equation here, dx, and it says to use substitution. Now, this one is a little bit tricky. So it's important when you get to questions that might be a little confusing looking to you, that you trust the math and just follow your normal procedure. So your normal procedure is to start with the u that they've provided for you and find the du. So the du is equal to 2 root 3x dx. And also what I like to do also at the beginning is to change the class or the bounds of integration from the variable x into variable u. So if you plug in a 1, you get root 3 for the top boundary. When you plug in a 0, you get 0 for the bottom boundary. This is now your boundaries for the variable u. So here's our integration with the change in boundaries. Now, when you look at the substitutions, this is where it gets a little bit interesting because none of the substitutions directly plug in. We got to manipulate some things a little bit. So notice there is an x dx and we have an x dx. So we need to get that by itself. And so our x dx equals 1 over 2 root 3 du. So that's this part right here, 1 over 2 root 3 with the du on the outside. We still have this 1 plus 3x to the fourth. If you notice, our u has an x squared. So if we solve for the x squared, we get 1 over root 3u, and then we can square both sides to make it x to the fourth, which gives us 1/3 u squared. So we plug in our 1/3 u squared for the x to the fourth. The 3 and 1/3 cancel, and that leaves us with 1 over 2 root 3 times 1 plus u squared. Now this still isn't very straightforward unless you happen to recognize it right away. Don't worry about the coefficient, this 2 root 3 on the denominator. Look at the 1 over 1 plus u squared. You do have an integral formulas that you can look through, and hopefully you recognize it as the inverse tangent of u. So have your formula sheet handy. Look for how to do the integral of a 1 over 1 plus u squared. It is not the ln. Might be tempting to think it's ln, but you can't do ln because the top is not the derivative of the bottom. This is the inverse tangent, and probably the easiest way to see it is when you look at the derivative of inverse tangent u, you will see this in the integral column. But this is what you need to identify, and now we're going to evaluate it from root 3 to 0. Plug in your root 3, and you get this. Plug in your 0, your inverse tangent of 0 is 0. By the way, at this point, you might be wondering what you should set your calculator to. There is not a domain statement. However, since you're going to want to use your trig function on your calculator, you're going to want to use radians because radians doesn't have a unit. Degrees has the little degree unit, and we don't have a way to process the degree unit. Radians is your non-unit unit. So actually, depending on the calculator you have, If you set it in radians mode, it's going to give you a decimal, but we're supposed to use exact area. So when you get the decimal, what I do is I switch it back to degrees. I get 60 degrees, and then I go, oh yeah, 60 degrees is pi thirds. So it kind of depends on whether your calculator gives you the pi thirds as a fraction or whether it gives you as a decimal, but you need to be able to recognize it. The exact value is pi thirds. So for me, I went with the degree and then converted it to fractional radians. Then plug that in. So this, by the way, I rationalized the denominator, multiplied top and bottom by root 3. So got root 3 over 6 times pi over 3, and that comes out to root 3 pi over 18. It is a good idea to rationalize your denominator because technically it's not proper to leave a radical in the denominator. So root 3 pi over 18 is your exact value. Now moving on to number 7, we have differential equations, quite obvious from the equation given, plus they tell it in the question. It's given that y equals 2 and x equals 0. Solve the differential equation, obtaining an expression for y in terms of x. This one is a bit challenging as well. First, you need to separate your variables. So separate, integrate, and then find your plus c. So we want to separate our differentials. The y minus 1, we're going to divide to the other side so it can be with the dy. The dx, we multiply to the other side so it can be with our x variable. Hopefully on the right-hand side, you need to realize that you cannot integrate that the way it is. You need to do partial fractions. So you need to go through your partial fraction procedure, which is from the further algebra part of P3. So you recognize the x plus 1 and x plus 3 as being simple denominators. And then if x equals negative 1, which cancels this, if you multiply everything by x plus 1, cancels here, leaving a by itself, cancels this out, cancels the x plus 1, so you're just left with 1 over x plus 3. When x equals a negative 1, you get 1 over 2, or a positive 1/2. When x equals negative 3, meaning you've multiplied everything through by the x plus 3, this cancels, leaving you the b by itself. You have x plus 3 up here. When you plug in the negative 3, becomes 0 and cancels this out. Your x plus 3 cancels this out, leaving your 1 over x plus 1. When you plug in a negative 3, you get a negative 2 on the bottom, so it's a negative 1/2. So here's positive 1/2 for your a. Here's negative 1/2 for your b, corresponding with these denominators. And now we can integrate that. On the left, you should recognize this as a ln y minus 1 equals on the right. You should also recognize these as ln as well. So you have 1/2 ln of x plus 1 minus 1/2 ln of x plus 3. Don't forget to put your plus c at the end because we don't have bounds of integration. Now I'm going to clean it up a little bit by taking the 1/2, making it the exponent, which when you have 1/2 as an exponent is the same thing as a radical. So these 1/2s become the radical of the argument. Now we want to find c. So we can combine these two together since they're on the same side of the equal sign with one of our laws of logarithms. When you subtract, you divide the arguments. When you subtract like logarithms, you divide the arguments. So we get this. And when we plug in our points for y equals 2x equals 0, we end up with 0 over here, ln 1/3 of root 1/3 plus c. So c equals negative ln root 1/3. Now that we plug that in for our plus c, Now we need to exponentiate both sides to start isolating our y variable. Cancels out over here, leaving you y minus 1. Over here, before I exponentiated, I joined these two logarithms together. Again, by dividing, when you divide by a root 1/3, same thing as multiplying by root 3. Since they both have radicals, the root 3 can join inside the radical and become 3 times x plus 1. So this minus means to divide, which gives us a complex fraction. You inverse and multiply by root 3. The root 3 then joins inside this root and becomes 3 times x plus 1. So the exponentiating both sides cancels out this logarithm, leaves us with the square root of 3x plus 3 when you distribute the 3 over x plus 3. Then just add the 1 to the other side. Here is our y in terms of x. Looks kind of ugly. That's why you need to trust the math, follow your proper procedure and your laws of logarithms correctly. Moving on to question 8a. Here we have into our complex number unit, given the equation that you see there. Solve the equation 1 plus 2i times w plus I w asterisk equals 3 plus 5i. Give your answer in the form of x plus iy, where x and y are real. So notice w is a vector, and vectors have the form of x plus iy. I put yi. And then the asterisk means it's the conjugate pair. So the conjugate pair has the same terms, but the opposite sign. So instead of x plus yi, it's x minus yi. Then multiply everything out. So use your smiley face method over here. You get x plus 2xi plus yi minus 2y. Don't forget that I squared is a -1. And then when you multiply your I through here, you get xi plus y, because your I squared makes -1, makes this positive. And your 3 plus 5i. Combine your like terms or your reals and your imaginaries together. So you get x, and notice there are two y's here. -2y plus y makes a -y. That's our real component. Then collect the imaginaries. Here's an xi, here's an xi. That gives us 3x plus y with the I on the outside. Here's the reals. The reals are equal to 3, and the imaginaries are equal to 5. So x minus y equals 3. That's equating coefficients. And 3x plus y is equal to the 5. Solve your simultaneous equations. I add these, get 4x equals 8, x equals 2. Plug it in over here. 2 minus y equals 3. Negative y equals 1, y equals -1. So you get 2 minus I is your vector. Now I put w because w was the vector in the equation that we're solving. Technically, we're solving for w. I'm not sure why in the mark scheme they use vector z, but we're actually solving this for w. So I used w as the vector is 2 minus x. Or I'm sorry, 2 minus I. Okay, moving on, we have an Argan diagram, which means graphing complex numbers. Shade the region whose points represent complex number z satisfying the inequalities absolute value of z minus 2 minus 2i less than or equal to 1, and the argument of z minus 4i is greater than or equal to a -pi4. So first I rearrange things a little bit. Z being our vector that we're dealing with. So we want to know z from what location. The from is your minus. Z from where? So factor out the minus, and that gives you a 2 plus 2i. And then you have a 1 over here. This is a circle where the 2 plus 2i is your radius, or sorry, your center, and the 1 is your radius. Or actually, 1, yeah, this is your radius out here. So here's the argument, z minus 4i. This argument is basically an angle. Z from 4i, and we're going to go to a negative pi force, which is a negative 45 degrees. So here is our equation. Here is our circle. Center is at 2 and 2i with a radius of 1. And then we have z from 4i, which is up here. And this is going to be the angle part, which you go down pi force. So from your imaginary x-axis, you go in the negative direction, pi force, which is negative 45 degrees. So it comes down through here, and it is within the circle, less than or equal to 1. So that's inside the circle and above our line. So shade this. And this line, by the way, is a half line. Don't draw the line through on this side over here. It is only a half line, kind of like a ray, starting from your endpoint and then going in the direction of this degree here, or measurement, angle measurement. So this is our Argan diagram. Now we want to go on to part II. Find the least value of mz, imaginary z, for points in the shaded region. So if we look at that, the lowest point in the shaded region for the imaginary axis is right here. Okay, that's the point that we're looking at that we want to figure out. That's the lowest point on the imaginary axis. So to do that, we know this point right here, it is the point 2 plus 2i, and we want to drop down to our lowest imaginary point, and we can make a little right triangle, and we know that the radius is 1. So if it's a right triangle where these sides are the same, here is our right triangle, sides are the same with hypotenuse 1, starting at the point 2, 2, that is over 2 plus 2i, we can calculate the value of x. Because these sides are the same, that means it's a 45-degree angle. Sine of 45 is opposite over hypotenuse. And when we calculate that, we get x equals 1 over root 2, which is root 2 over 2. So we want this 2 right here, the second one, the y-axis 2. And then we're going to come down, we're going to subtract the root 2 over 2. So 2 minus root 2 over 2, or if you combined it as one fraction and made it 4 minus root 2 over 2, they're both the same thing. This is the exact value for the point right here, starting at 2 on the y-axis and dropping down a negative root 2 over 2. Moving on to number 9, shows this diagram. It is the curve cosine x, which is this part, and the curve y equals k over 1 plus x, that's this part. For the domain of 0 to pi halves, again, note that this is radians, so set your calculator back to radian mode, and the curves touch at point P, or when the x is at P, which is this point up here. So show that P satisfies the equation tan P equals 1 over 1 plus P. If you look Further, you notice this is an iteration or iterative formula type question. And in those kind of questions, the first part of the question is usually some sort of a algebraic manipulation of something that you learned in the past. So we got to figure out how to come up with this form. Well, one of the things that you probably would recognize is that these two equations meet or intersect at this point. So you set one equation equal to the other, and you can get it down to probably this point right here. Sine x equals k over 1 plus x squared. And that's kind of where you stop. When you look at this and you look at this up here, you can't just divide by cosine to get your tangent, because then you'd have to divide by cosine over here. Doesn't really help us to get this right-hand side of the equation. So this is the tricky part. Not only when they intersect does that mean that they are equal, but since they're both on curves and they meet there, it also means that the slope is the same for both at that point. And slope is your first derivative. So if we come back here and we do, this one right here, when you simplify the original, this one equals this one, it kind of stops here. I said it stops down there, stops right here. Then that's for the point being equal on both graphs, but also the slope is equal, so you need to do the derivative. So the derivative of cosine is a negative sign. The derivative of this over here, move the denominator up. This is our variable that we're deriving. The negative 1 multiplies to the front. Subtract 1 gives you your negative 2, which moves it downstairs as a 1 plus x squared. And there is no derivative on the inside, or I should say the derivative of the inside is just 1. So you don't have to worry about that. If you solve for k, you get k equals sine x times 1 plus x squared. Now, if you plug that in for k into our original, you get this, and notice that one of the square, one of the factors cancels with the factor here on the bottom. So notice we substituted this in for k and canceled out one of those factors, top and bottom. That leaves us with this. Now you can divide the 1 plus x to the other side. Now you can divide the cosine to the other side to get your tangent. So you get your tangent x equals 1 over 1 plus x. Substituting in your x equals p, which is right here, gives you the tan p equals 1 over 1 plus p. So it was a little bit tricky. Again, I think most students would recognize, because they intersect, you can make this equation, but hopefully you also recognize that you can also do the slope of both sides and they will be equal. Slope being derivative. Now, part B, use the iterative formula, where, remember, it's x equals f of x in your iterative formula. In this case, p equals f of p, function of p, where our function is the inverse tangent. It's already set up for you. P is already by itself. So I started with 0 simply because 0 is the left-hand border, and we want to get to p, the value of p. So start with 0. Remember to take your iterations to 5 decimal places, and you're looking to get a correct value accurate to 3 decimal places. So plug in the 0, comes out to 0.78540. Plug that back in on your calculator. You can just put answer. Once you got your first answer, you can put answer here so you can go a little faster in it. So your second iteration is here, third, fourth, fifth, all the way up to your eighth. And you want it accurate to 3 decimal places. Right here, you have 7.3. Here you have 7.9. So you're not sure if it's going to round up or round down. And then when you do this one, you can see that obviously the 7 will be rounding up. So it's 0.568. Hence, find the value of k correct to 2 decimal places. So this value of p is what we have in here for our k equals. Remember, our x equals p. So we plug in the value of p for that k expression. K equals, there's our sine x, 1 plus x squared. Plugging in the 0.568 for the x's, comes out to k equals 1.32. Question 10, with respect to the origin, the points A and B of position vectors, OA is 6i plus 2j, OB is 2i plus 2j plus 3k. The midpoint of OA is M. Find, or the point N is on AB between A and B such that AN equals 2 and B. Find a vector equation for the line through M and N. So we have OA already given. OM is just taking half of OA. So it's 3i plus j. Okay, OM is the midpoint, so it's just half of OA. So half of 6 is 3, half of 2 is 1. For AB, which it talks about line AB is OB minus OA, the position vector of B minus the position vector of A. So we have both of those. 2 minus 6 is a negative 4. 2 minus 2 is 0. And then 3 minus 2 is, 2 minus 2 is 0. 3 minus 0, there's no k over here. So it's just 3 minus 0 is 3. So we end up with a negative 4i plus 3k. Make your AB line. N is on the line AB such that AN equals 2 times NB. So AN is 2 times of NB. So that means there's 3 pieces total. So AN equals 2/3 of AB. And our AB was up here. So we take 2/3 of that. Gives us a negative 8/3 I plus 2K. And AN also equals ON minus OA. ON minus OA. So ON is AN equals ON minus OA. Solve for ON. ON equals AN plus OA. So to get ON, we want to do AN plus OA. Negative 8/3 plus 6 gives us 10/3 I plus 2J plus 2K. And then we want to find MN. MN is ON minus OM, N minus start. And take those two and subtract them. You get 1/3 I plus J plus 2K. So now we can make our vector equation of our line. And I'll just use the point 310, which comes from, where did our, right here, the OM. 310 is our OM, 310 plus mu times the direction of MN. which is 1/3, 1, and 2. Now, what I did is instead of putting a fraction in, I factored out that 1/3, divided out the 1/3, and put the 1/3 in with this constant. This constant is really any multiple of these numbers. So when I factor out the 1/3, that leaves us with 1, 3, and 6 as these direction of the line. And if you rewrite it in component form instead of this column vector form, you get r equals 3i plus j plus mu, which is this part, or just 3i plus j, there's no k, then the plus mu times I plus 3j plus 6k. So there are several different ways of writing the equation, but these two both would be correct. Going on to part B, the line through M and N intersect the line through OB, find the point at the point P, find the position vector of P. So our point B was, OB was 2, 2, 3. OB is 2, 2, 3. So that's right here. And O is the origin. So R equals O plus lambda times 2, 2, 3. And this equation here of line MN is what we just found right here. So we're going to put the x, y, and z of this one set equal to the x, y, z of this OB one. So here is 3 plus 1 mu, 3 plus mu equals 2 lambda. And then we have 1 plus 3 mu equals 2 lambda, and then we have just 6 mu equals 3 lambda. Okay, so the 6 mu comes from this. There's no k, so there's 0 plus 6 mu equals 3 lambda. Solving for lambda, lambda equals 2 mu, where mu is 1, because we plug in our 2 mu into one of these here. Lambda equals 2 mu, plug it in, 3 plus mu equals 2 times 2 mu. Solve for mu, mu equals 1, plug it in here, lambda equals 2. You can also, it wants to find the position vector of B. So OP equals, OP are OP. Okay, they intersect. We just solved for the point of intersection. By solving these simultaneous equations, we got lambda and mu. So when we plug them in, the 1 for the mu's, the 2 for the lambdas, we get 4, 4, 4, 4, and 6, 0, which means that they are consistent, and that's our coordinates of intersection. So OP would be 4i plus 4j plus 6k. That is our position vector for point P. Now we want to calculate angle OPM. So remember, you can either work from the middle variable out or from the outer variables in. So I have OP dot product MP equals the magnitude of OP times the magnitude of MP cosine theta. We want to find the answer in degrees, so make sure your calculator's in degree mode. OM, we need to find MP. MP is OP minus OM, and when we get that, we get I plus 3j plus 6k. Magnitude of MP is this here, which comes out to root 46. Magnitude of OP, which is this here, comes out to root 68. And then we use our M or our OP 446, and our MP 136, and we do 4 times 1 plus 4 times 3 plus 6 times 6. This is the left-hand side of what's called your dot product or scalar product rule. This formula is also in your Cambridge formula sheet. So you multiply 4 times 1 plus 4 times 3 plus 6 times 6. That's the left-hand side, which equals 52. The right-hand side, we put in these radicals, 68 and 46. We're solving for cosine theta. So we inverse cosine theta of 52 divided by root 46 and root 66. And that angle comes out to 21.6 degrees. And that takes us to the end of this paper 32 of Pure Mass May-June series 2020. I hope it was helpful for you to understand the questions. As always, thank you for joining me, and I hope to see you again next time.